Welcome to our presentation on Scalable Nearest Neighbor Search for optimal transport. Let's start with an overview. We introduce Flowtree. It is a fast nearest neighbor search algorithm for the optimal transport distance, also known as the Earth mover distance or the Razenshteyn 1 distance. It is a linear time algorithm with worst-case approximation guarantees for nearest neighbor search. It speeds up state-of-the-art nearest neighbor search in the optimal transport distance by a large factor, and our code is online. We put a lot of effort into making it both fast and usable, and we implement not only Flowtree but also all of the baselines mentioned in this talk, so we hope you will check it out. Let's define optimal transport. First, suppose we have 2 points in R2D. We have many standard ways to measure distance between them: Euclidean distance, Manhattan distance, and so on. But what happens if we want to measure distance between 2 sets of points? So we have a blue set capital X and a red set capital Y, and we want to define a notion of distance between the sets. So we are going to choose a distribution over each one of the sets, and for this talk they are going to be uniform distributions, even though in general they don't have to be. And the optimal transport distance is defined as the value of the minimum cost flow from the blue points to the red points with the demands specified by those distributions. This means we consider the bipartite graph between the blue points and the red points, and we solve minimum cost flow on this graph and return its value. The value is the sum of the flow on each edge times the cost of the edge, and in this case the cost of an edge is the Euclidean distance between its endpoints. So this is optimal transport. It is a very popular notion of distance between sets of points and between distributions, and it has many applications in machine learning and data analysis. Let's see one motivating application, for example. This is a notion called word mover distance due to Kushner et al., and they suggested using optimal transport as a measure of semantic similarity between text documents. For example, we have 2 sentences. Obama speaks to the media in Illinois, and the president greets the press in Chicago. These sentences don't have any overlapping words except for stop words, so to many classic algorithms it might seem like they don't have anything to do with each other, even though to a human reader it is obvious that they mean basically the same thing, at least back in 2015 when this paper was published and Obama was president. So Kushner et al. Suggested the following. We are going to embed the words from both documents in R2D using word embeddings, which are high-dimensional representations of individual words generated by neural networks. So we embed the blue words and the red words, and now we can measure the optimal transport distance between them and use this as the distance between the documents. And Kushner et al. Show that this gives you a very high-quality notion of semantic similarity between text documents. In order to utilize this notion, we often need to solve nearest neighbor search. The setting is that we have a dataset with many documents which are labeled, and we have a new document that we need to label. So we measure the distance from the new document to each document in the dataset, and in this case it's the optimal transport distance, and we find the nearest document and give them the same label. This is the nearest neighbor classifier, and even though it gives you very high accuracy, it does not scale to large datasets, because computing even one optimal transport distance means solving an optimization problem, minimum cost flow. You can do this exactly by linear programming or by even faster methods specialized to flow problems, but still, the exact computation is not feasible for large datasets. So naturally, there has been a lot of work on approximation algorithms, and we can generally place previous work on 2 ends of this imaginary axis. On one end, we have linear time algorithms. They are very fast in practice, but they only give you a crude approximation of the true distance. And on the other end, we have quadratic time methods. They are much slower, even though they are faster than exact computation, and they give you a very close approximation of the true distance. The question is, do we have to make this compromise, or maybe we can somehow get the best of both worlds? And this is basically what we do here. Flowtree is a linear time algorithm. It is not as fast in practice as the other linear time methods for reasons that I will mention, but it is much faster than the quadratic time methods while getting the same quality of approximation. So let's see the algorithm. It is based on a classic algorithm called Quadtree, which is very useful for many geometric problems, including optimal transport. And I'm going to show it here in 2 dimensions, even though it works in every dimension. So suppose we have our input blue and red points. The first step is to enclose them in a big hypercube, and we choose the side length delta to be large enough to enclose all of the points. For reasons related to the analysis, we also shift this hypercube at random. Then we start constructing the quadtree. The root contains all of the points, and in the next level, we split the hypercube along each dimension exactly in the middle. So we split it into 2 to the d sub-hypercubes, and we add the non-empty sub-hypercubes as nodes to the tree. In the next level, we repeat this for every hypercube that contains more than 1 point. and so on until eventually each point is contained in its own hypercube and forms a leaf in the tree. And this is our quadtree. So how do we use the quadtree to approximate optimal transport? We are simply going to compute the optimal flow in the tree. And computing the optimal flow on this tree with those edge weights turns out to be a linear time algorithm that can be done by a simple greedy bottom-up process. So let's see an example. In the bottom level, we greedily match the blue and the red points on the right, and we have some excess blue demand that cannot be matched and goes to the next level. In the next level, we greedily match the blue and the red points on the left, and again we have some excess blue demand. And in the top level, we match the excess blue demand with the red demand in the middle, and this is our flow on the tree. And we simply return its value, which is the sum of the flow on each edge times the weight of the edge. So this is already a fast linear time algorithm, but this gets even better. It turns out that using this quadtree, you can define a red vector and a blue vector, and this value of the flow that we return is equal to the L1 distance between those two vectors. So the whole quadtree algorithm for optimal transport reduces to computing one L1 distance between two sparse vectors, which is a very fast operation in practice. So this was quadtree, and now let's see our modification of it that we call Flowtree. We are still going to compute the same flow on the tree, but we are going to evaluate its cost with respect to the original metric space. What does that mean? We go through the same greedy bottom-up process to compute the flow, but we also keep track of the corresponding flow in the original space R to the D, and in the end we return the cost of this flow in R to the D. So it's the sum of the flow on each edge times the Euclidean length of the edge. And this is exactly like original optimal transport, except that we use the flow computed on the tree instead of the optimal flow. So this might look like a small modification of quadtree, but it actually leads to an algorithm with very different properties. So let's compare them. In terms of running time, quadtree is linear time, and it also has this cool L1 embedding property, which makes it very fast in practice. Flowtree is also a linear time algorithm. Asymptotically they are the same, but it doesn't have this embedding property, so it is not as fast empirically. In terms of the approximation factor for nearest neighbor search, quadtree depends logarithmically on those four parameters, d, delta, s, and n. Let's recall what they are. So n is the number of documents in your dataset, s is the maximum number of words in a document in your dataset, and d is the dimension of the word embeddings. And delta is the side length of the hypercube at the top of the quadtree. As you can see here, the problematic parameter is n, because the number of words in the document s and the dimension of the word embeddings d are usually not more than a few hundreds, while the number of documents in your dataset n can be much, much larger. And this dependence is actually necessary for quadtree. You cannot get rid of it. On the other hand, Flowtree has the same approximation factor, but without the dependence on n. And this is related to the fact that Flowtree never underestimates the true optimal transport distance. It can only overestimate, so it only has one-sided error. And if your distributions are uniform, which is the case in the word mover distance, then this gets even better. The approximation factor is also independent of the dimension and of delta, and depends only on s, the maximum number of words in a text document. So let's see some experiments. We use the 20 newsgroups dataset, which is a standard benchmark dataset for text documents. So first, let's evaluate each algorithm individually. On this plot, you see the recall at k accuracy, which is the fraction of queries for which the true nearest neighbor is ranked in the top k neighbors by the algorithm for increasing values of k. So on this plot, you see the linear time methods. They are very fast in practice. They run in milliseconds, but they only give you that quality of approximation. And on the right plot, you see the slower methods. They are much slower. They run in seconds and not milliseconds, but they are also much more accurate. For example, to hit 90% accuracy, to find the true nearest neighbor for 90% of the points, on the left plot, you need k to be something like dozens or hundreds, whereas on the right plot, you need k to be less than 10. And as you can see, Flowtree is much faster than the quadratic time methods by at least a few times, while getting similar accuracy. Our next set of experiments are pipeline experiments. What does that mean? As we've seen, we have a very sharp divide between the fast and the crude algorithms to the slow and the fine algorithms, and this motivates combining them together into one system in the following way. We first feed the whole dataset into a fast and crude algorithm, and this algorithm is not accurate enough to report the nearest neighbor, but it is accurate enough to prune out some of the least promising points. Then we feed the prune dataset into the second algorithm. It is a slow algorithm, but it runs on a smaller dataset, and it is more accurate, so it prunes the dataset even further. And in the end, maybe we perform a small number of exact optimal transport computations on the few surviving points. And then we report the nearest neighbor. This is a nearest neighbor pipeline. They are very useful in practice. So this set of experiments is for weakolet 1. It means that we require the pipeline to report the true nearest neighbor for at least 90% of the queries. The first step in all of our pipelines is going to be Quadtree, because according to our experiments, it is by far the best choice for the first step. And in the baseline pipelines, in the second step, we use one of the quadratic line methods mentioned before. So RWMD and ACT are two variants of the greedy algorithm, and Synchron is the popular synchron iteration algorithm of Quadtree, with either 1 or 2 iterations. So adding iterations doesn't help here. And the final step is the necessary number of exact optimal transport computations to find the true nearest neighbor for at least 90% of the queries. So each pipeline is indicated by a vertical bar, and on the vertical axis you see the time in seconds that each step in the pipeline consumes. Then we introduce Flowtree into the pipelines in one of two ways, either as an intermediate step between the first and the second algorithm, or as a replacement for the second algorithm. And you can see in all cases we get speed up overall by a factor of about 3.7 in the running time. The final experiment is for weakolet 5, so this means that we only require the pipeline to rank the true nearest neighbor in the top 5 for 90% of the queries. We look at the same baseline pipelines. This time, because the recall goal is easier, Synchron is actually accurate enough that it doesn't need any exact computations following it in the pipeline. And this allows us even greater gains when we introduce Flowtree into the pipelines, this time by a factor of about 7.4. So this is it. Let's conclude. We introduce Flowtree for nearest neighbor search in the optimal transport distance. We show it is useful both analytically and empirically, and our code is online. Thank you.